Keep watching to the end of this video. If I tell you to imagine a telescope, what do you see? Perhaps you picture an old wooden cylinder with lenses at both ends, similar to one that Galileo Galilei first used to gaze up at the heavens and see the moons of Jupiter. Or maybe your mind is constructing a cathedral-sized dome with mirrors as big as tennis courts, like the telescopes high up in the mountains of Chile and Hawaii. Or you could even be drifting onto visions of enormous dishes, like the infamous Arecibo telescope that once captured radio waves from across the cosmos. What you probably aren't imagining is a cubic kilometer of ancient ice under the surface of our planet's South Pole. And yet, deep below the frigid landscape of Antarctica, there lies precisely this, a strange telescope in one of the most inhospitable environments on Earth, designed to observe, not light, but instead one of the most unusual and elusive particles in the universe. I'm Alex McColgan, you're watching Astrum, and today we're joining the IceCube Observatory in its hunt for neutrinos, also known as ghost particles. If you stood on this icy surface, you might not be aware that some of the rarest events in the universe are being observed beneath your feet. Located at the most southerly human-occupied base in the world, the Amundsen Scott South Pole Station, IceCube makes use of the very ice in which it is built to observe high-energy neutrino particles. But why? Why this extreme environment and weird design? Because neutrinos are weird. Really weird. Neutrinos are fundamental particles, like quarks and electrons. Most of these neutrinos arrive at Earth from the Sun, where they are released from the nuclear fusion reactions raging inside its core. Other neutrinos will have come from more cataclysmic origins, such as a supermassive black hole, supernovae, or any other cosmic event with enough energy to rip atoms into their subatomic particles. Similar to electrons, neutrinos belong to the lepton family of particles, meaning that they do not interact with other matter through the strong nuclear force that binds other subatomic particles like protons and neutrons together. Unlike electrons, they are neutral and have almost no mass whatsoever. This lack of charge and tiny mass means that they can only interact with other particles through the weak nuclear force, giving them their ghostly quality and making them one of the most difficult particles for scientists to detect. So much so that even when we do measure their presence, it is only through the impact they have on other particles. If that wasn't spooky enough, neutrinos can also pass through our entire planet without acknowledging the existence of a single atom in the crust, mantle, core, or any other layer of the Earth, flying straight out of the other side completely unnoticed. There are trillions of neutrinos surging through you every single second. And yet, over your entire lifetime, there is only a 1 in 4 chance that even one of those neutrinos will interact with an atom that belongs to your body. Most of these neutrinos are arriving at Earth from the Sun, where they are released from the nuclear fusion reactions raging inside its core. Other neutrinos will have come from more cataclysmic origins like supermassive black holes, or supernovae, or any other cosmic event with enough energy to rip atoms into their subatomic particles. Here we find further demonstration of the neutrino's complete refusal to engage with matter in the universe. Photons, created in those same nuclear reactions, may take 1 million years between bursting out of the sun's center to leaping off the surface into space. They are constantly absorbed and emitted in random directions over and over again by the atoms in our star, resulting in a long meandering path to escape. Neutrinos, instead, zoom straight out of the sun in just 2 seconds, traveling at almost the speed of light itself. As far as standard model particles go, neutrinos are certainly the more coy and antisocial of the group, but on occasion they do mingle with other matter, and in the process, can create a drama of energetic particle events cascading out in their wake. It is this cascade IceCube is trying to observe. Suspended down between 1.5 and 2.5 kilometers in the darkness of the ice shelf are 5,160 detectors arranged into a lattice cube. Down here, the sun's rays have been completely swallowed up by the thousands of meters of compressed ice that lie above, and yet, these detectors, called DOMS, are in fact light detectors. I already said that this telescope is not observing light, at least, not direct light reaching us from sources far out in the universe. Neutrinos are so elusive, the DOMS must detect them indirectly, by taking advantage of a cascade of reactions that starts with a neutrino colliding with an atom of frozen water and ends in a blue flash. When the DOMS detect a blue flash, The scientists know that either a cosmic ray or a neutrino has passed through the ice, and the hunt begins to find its cosmic origins. The key step in this cascade, and therefore the key to identifying a neutrino interaction, is the muon particle that springs out of the initial collision between neutrino and ice. As the newly created muon hurtles through the incredibly clear and dense ice, it can exceed the speed it takes light to move through that same ice. Now let's be clear, nothing can move faster than light in a vacuum. But in other materials, such as ice, liquid water, and glass, light can be outpaced. This isn't a violation of physics, but rather a consequence of light slowing down more than other particles within the ice. As the muon races beyond its photon counterparts, it generates a shock wave of blue light expanding in a cone-shaped pattern out from its path, an eerie phenomenon known as Cherenkov radiation. Cherenkov radiation is most commonly associated with nuclear reactors, eerily emanating through the water that surrounds their cores. This blue hue in nuclear cores and strangely also down in the ice of the South Pole can look peaceful and atmospheric, but is in fact the quantum equivalent of the sonic boom that roars out from a supersonic jet plane flying overhead. In this case, the plane moves through the air, pressure or sound waves are pushed out in all directions. With the jet's speed building up towards the speed of sound, the waves in front start to bunch up, forming a shock front of high pressure. When the plane exceeds the speed of sound, it smashes through the shock front, causing a rapid change of air pressure. This is the sonic boom. The shock front then travels out in a cone, trailing behind the aircraft, which observers will hear as a thunderous clap. In the case of the muon, the particle is not pushing air, but instead disturbing the electric fields of atoms in the ice with its electromagnetic charge, polarizing the water molecules. As the molecules depolarize back to their usual state, they release the energy that forced them into polarization as photons of blue light traveling out in all directions. This is happening all along the path the muon takes through the ice. The traveling muon is triggering emission of electromagnetic waves from the water ice molecules, which radiate out into all directions, producing a cone of emission in the direction of the muon's motion. If the muon was traveling slower than light in the ice, there would be no wave front, and all the expanding light spheres would destructively interfere with each other, canceling out to complete darkness. But since the muon is traveling faster than light, a shock front of constructive waves in the form of blue light is created. The thousands of digital optical modules of IceCube are primed to detect this signature blue light flashing through the ice. The minuscule time differences between when one DOM registers the flash and when the neighboring DOMs detect it allow the scientists to triangulate the neutrino and trace its path back through the ice, and ultimately through the universe to its origin. These orb-like detectors are marvelous, intricate devices designed to detect the faintest luminal hints in the icy mass. Each DOM is encased in a 13-inch spherical glass pressure case, which protects the electronics inside from the extreme cold and high pressure of the Antarctic ice. Botner et al., 2005. Inside, there is a photomultiplier tube sensitive enough to detect even a single photon, along with various components that amplify the signal and convert it into digital data, which is then transmitted up the cables to the surface. And with so many detectors making up this three-dimensional array, there is a lot of data. A whole terabyte of measurements are captured every day, with 100 gigabytes of that being beamed by satellite to scientists across the planet, for them to comb through in search of their ghostly quantum target. Within this trove of data lie the imprints of many particles arriving from beyond our atmosphere. The vast majority are cosmic rays. IceCube detects around 275 million of them daily. Cosmic rays are interesting in their own right, but serve as an obscuring curtain of noise to those seeking neutrino interactions, which occur a million times less frequently, with only around 275 detected daily. But even with the 100,000 neutrino detections that IceCube makes each year, almost all of them are generated in our own atmosphere as debris from collisions of cosmic rays with atoms in the gas that surrounds our planet, and not from cosmic origins themselves, the key word here being almost. On the 22nd of September 2017, an exceptionally bright burst of Cherenkov radiation was registered by IceCube's array of detectors. Working together, the DOMs used the tiny time differences between when they each detected the flash to trace the path of the muon and the exceptionally energetic neutrino that created it, all the way back to a powerful and mysterious cosmic source out in the depths of our universe. A blazar, a supermassive black hole at the center of a distant galaxy, hurling jets of particles towards Earth. This discovery was monumental. It was not the first time that IceCube had detected neutrinos from deep, deep space, but this detection was the first to trigger a real-time alert to telescopes across the globe, indicating that there was something significant to look at in that direction. IceCube and neutrinos had entered the world of multi-messenger astronomy, where the cosmos is studied through not just light, as it has been for most of the history of astronomy, but also gravitational waves, cosmic rays, and now neutrinos. Neutrinos are a particularly useful window for us to look through because, like gravitational waves, they can arrive at us before the light from a major astronomical event does. Because of their ghostly nature that I talked about before, neutrinos take a very direct path to our detector, whereas light faces many obstacles like dust and magnetic fields that interfere with its journey and slow it down. IceCube is now fully integrated into a planetary network of observatories, constantly scouring the skies for signs of high-energy events, ready to inform radio dishes, mirrors, and lenses precisely where to point to see rare and transient phenomena that we would otherwise miss completely. IceCube is the noble watchman, sounding the alarm to rally an army of telescopic troops across the globe, commanding them where to aim to catch sight of raging cosmic fires. And even further than that, IceCube can give us a unique view into the heart of these phenomena. Because again, unlike photons, neutrinos can escape relatively unscathed from high-energy environments, such as the core collapse of supernovae explosions or cataclysmic mergers of unfathomably dense neutron stars, or even the searing fury of supermassive black holes. IceCube can deliver new and different information. It can see things light-based telescopes are blind to, so to speak. The neutrinos it detects can hugely broaden our understanding of all these events and of the most fundamental nature of the universe. During these events, physics is pushed to its limits. Particles are accelerated to speeds and energies thousands of times greater than what we can achieve in our particle accelerators on Earth, like that of CERN. This allows physicists to test their theories and use the arrival of neutrinos at IceCube to make new discoveries not only about the behavior and properties of neutrinos, but also about dark matter and even about ice itself. This is why so much effort was put into building such an extreme telescope as the IceCube Neutrino Observatory. An effort that took 7 years to complete, with work pausing during the Antarctic winter when planes are shut out from Earth's most southerly continent by the brutal weather, only able to briefly resume for the summer months of November to February. Over those 7 years, the IceCube team drilled 86 holes 2.5 kilometers deep, using 18,000 liters of fuel per hole, and melting 750,000 liters of ice in the process, all to have a few hundred scientists live and work in one of the most inhospitable environments on our planet in an attempt to understand the most extreme events in our universe and to capture a glimpse of the most elusive particle in the universe. Neutrinos are the phantoms of the particle kingdom. It takes bold and ingenious ideas from ambitious scientists to witness even a single one neutrino. We know so little about them compared to other particles, but they are just as important in furthering our understanding of the fundamental laws of nature. With each neutrino detected, we are moving closer to comprehending the universe and the powerful forces that shaped it. Our solar system is filled with the beautiful, the inspiring, and the complex we love.